in chapter exercise 6. So I gave it a try, and well, other than the sixth question, everything else is just very mediocre. So everything else, I mean, you can just prove it by yourself. But the sixth question, it's like really good. Anyway, let's start doing it. So first question. So you have to prove that C1 upon C0 plus 2 C2 upon C1 all the way to till n. This is equal to n times n plus 1 upon 2. Now you can use the fact, I mean, it's just basically like summation of r plus 1, I guess. Yeah, r plus 1. And then you have, well, in fact, let's not do that. Let's just go with r. So summation of r CR, and then so NCR basically upon NCR minus 1, right? It goes from 1 till n, of course. And yeah, so this whole thing can be written in a different way. So this can be written as n minus the smaller number, which is r minus 1. So minus r plus 1, and that upon the bigger number, that is r. So r times this thing is just n minus r plus 1. So it's just summation of this quantity. Summation of n minus r plus 1 as it goes from 1 till n. So yeah, let's start putting 1 in it. So when you put 1, just get n, then you get, so you put 2, you get n minus 1, and then so on. And when you finally put n, you just get 1. So we know what this series is. It's just n into n plus 1 upon 2, right? So sum of the first n natural numbers, that's why this thing. So the first one is mediocre. Yeah, let's just not put these symbols because all of these are just going to be proof questions. Go for the second one. C0, C2, C1, C, right? So this is just I think it's called Vandermonte's identity, whatever. Yeah, so this is like NC0, NC n minus 1, and then you got NC1, NCn minus 3. Yeah, I guess, and then you got NC2, NCn minus 4. So look at this plus that, it's got 2, and then you got 4, huh? Oh, it's 2, sorry. Initially it's supposed to be 2. Right. So look at this. 0 plus n minus 2 is just n minus 2. 1 plus n minus 3 is n minus 2, and then so on. So all of these are just n minus 2. So basically it's like you are choosing n minus 2 people out of n females and n males. So like you have a complete group of 2n people, but n of them are males and n are females. So you want to choose n minus 2 people out of these 2n people. The number of ways to do that is of course just 2n c n minus 2. But what you could do is that you could say we will choose 0 males and then n minus 2 females, or you could choose 1 male or n minus 3 females, and so on. And that's how this series becomes equal to that. There's also a different way of doing this, which is also, I mean, it's pretty combinatoric, but it's more algebraic than this. Just saying that it is equal, right? So the way to do is just consider, well, 1 plus x power n, and then 1 plus x power n again. So which is going to be 1 plus x power 2n. So now if you want to if you want to have the coefficient of x power n minus 2 from here, what you can do is you can expand this out completely, right? So it's going to be like 1 plus nc1x plus nc2x square, whatever. Then you can expand this out. So 1 plus, yeah, the same stuff, right? And then what you can do is you can, I mean, you know, like in the multiplication, it's going to be one term from this bracket and one term of these from this bracket, all of these terms combined, and then you recombine them when you simplify. So since we want n minus 2, we could just start off at 1. So the first term, which is basically is nc0. So nc0, well, that times whatever term has x power n minus 2 from the second bracket, which is going to be nc0, nc n minus 2, and then yeah, the next will be nc1x, and that times whatever term has x power n minus 1 from the second bracket. So it's going to be nc n minus 1, and then yeah, you get the idea, right? Oh, whatever term has, sorry, x power n minus 3 from the second bracket. So nc n minus 3. So that's why nc1, nc n minus 3, and so on. And yeah, this is the way that's it's generally taught, and for good reason, because it's more usable than the normal combinatoric argument. So the second one, it makes sense why this is just 2nc 2nc n minus 2, right? And this is exactly that. So 2nc n minus 2, 2n factorial, n minus 2 factorial, and then the 2n minus n minus 2 factorial, right? Which is just n plus 2 factorial. Okay, let's go to the third one. So NC0 n plus 1 C1 NC1 n plus 1 C2. So now you can see the pattern. This is going to be NC0 n plus 1 Cn, and then you got NC 1 n plus 1 C n minus 1 and so on. So now it's just obvious that it's going to be n 2n plus 1 C n, right? So it's like choosing n people out of 2n plus 1 people, n of them are male, n plus 1 are females, right? So it's going to be 2n plus 1 Cn, and that's this thing, right? So and you will just break this into n and n plus 1, and that's why 2n factorial upon n factorial n plus 1 factorial. Exactly. Yes. Now this has nothing to do with this being n or n plus 1, right? That's not important. If this was something else, it was m, then you just have 2n plus 1 Cm, right? So don't get confused by that. It's just coincidental that here you have n, not necessarily the case all of time. Okay, so the fourth one, right? That's what we did. No, we did the third one, right? Now let's go to the fourth one. So it's got C1 squared plus 2C2. Now look over here. It's a little different, you know. Yes, so here you have this 2, 3 and so on, this extra stuff. So there's a way of doing it combinatorically as well, but before that you have to do a bit of algebra. So you can write this as like S is equal to so we'll just start off at 0, in fact, not 1. So this will be 0 C0 squared plus 1 C1 squared and then so on till you eventually get n Cn squared. But you can also write this in the opposite order. So n Cn squared plus n minus 1 C n minus 1 squared and then so on till you eventually get 0 and 0 C0 squared. Now this is not n Cn, no, it's n times Cn. Okay, and then you can add this up. So notice the fact that C0 and Cn, well, they are the same thing in fact. So this is like 2s is equal to n times of C0 squared plus C1 squared and so on till you eventually get Cn squared, right? So all of these will just have the n factor and it will be out. And that means s is equal to n upon 2 times whatever this thing is. Now this is doable because it's just like nc0 squared, just nc0 and then once again nc0, but we'll write that as ncn and then nc1 ncn minus 1 and you get the idea. So this is just going to be 2ncn. So there we go. So this is going to be n upon 2 times 2ncn. So that's just n upon 2 times 2n factorial upon n factorial n factorial. Now you can take 2n and out of these things. This will be like n upon 2. We got 2n right there, we got n squared here, now we got 2n minus 1 factorial and then n minus 1 factorial squared. Now this cancels, just get this thing. So fourth one is also easy, it can be done. What about the other way? So not using the identity directly but using something else, right? So notice it's got like 2 and 3 and so on, right? So we know that 1 plus x power n is just C0 x, I mean whatever they said, right? This whole thing, what we can do is just differentiate this guy. So once you differentiate, just get n into 1 plus x power n minus 1. That's just equal to C1x, so that's gone actually, C1 plus 2C2x and yeah, so the usual stuff. But now what we will do is that we'll multiply this whole equation by 1 plus x power n again. Okay, cool. And now we'll just n minus 1 over here. Okay, and now our task will be to figure out what's the quotient of x power n minus 1 in this thing. So C1, we need to combine C1 with Cn minus 1, and that's why we'll have the quotient of x power n minus 1 as our goal, right? So that you will get C1 that times Cn minus 1 x power n minus 1, which is like C1 squared x power n minus 1, and then you will get 2C2 and what do we have? 2C2 and then you got Cn minus 2 x power n minus 2, and then of course this x was also there, so that will give us that x power n minus 1. And yeah, so just want the x power n minus 1 coefficient from this guy, so from basically this guy 1 plus x to the power of 2n minus 1. So now it becomes clear, it's just going to be n 1 minus 1 Cn minus 1. Now good thing is, I mean whatever, just write it like that. So it's going to be n times, but hopefully this makes sense. Okay, so just 2n minus 1 factorial upon n minus 1 factorial and I got n factorial. So n and n factorial, you can see the thing, it's going to be this thing squared, but that is gone now. And that's exactly what this is. So in that way as well, it's doable. The next question. So summation from k is equal to 1 till n of k cubed and ck upon, so once again ck upon ck minus 1, we can deal with that very easily. So it's going to be what? N minus the smaller numbers, n minus k plus 1 upon the bigger number. So that's just k, this thing squared. That times k cubed, alright, not squared. So this will be just, yeah. So we want to sum this up from k is equal to 1 till n. Now, what we can do is that instead of going from k is equal to 1 to n, we can use r, where r will be this whole thing. So I'll call this whole thing as r. So then you just have k is equal to n minus r plus 1, right? Now this will just become summation of r squared and then n minus r plus 1. But from where to where does r go? When k is 1, so r is just basically n minus k plus 1, right? Okay, so when k is 1, r just becomes n, and finally it becomes 1. So I will not write it like that. I will write it 1 to n, because in the end both mean the same thing. And yeah, there you go, you got this thing. So it's like summation, so n plus 1 effect, n plus 1 take out, summation of r squared, okay, from 1 to n, and then minus summation of r cubed from 1 to n. So that's doable. This is going to be n plus 1 times n plus 1 times 2n plus 1 upon 6, and then minus of n squared into n plus 1 squared upon 4. Now let's calculate. So you got n plus 1 squared common, and then this and that, and then you also have a 2, the denominator common, so you can take that out. So n plus 1 squared upon 2, and now in the bracket just have n times 2n plus 1, which is like 2n squared plus n, and that upon 3 minus n squared, I mean, yeah, just n squared upon 2. So that will just be 4n squared plus 2n minus 3n squared. So n squared plus 2n, right? So n plus 1 squared times, we'll just do it once again the normal way. So plus 2n minus 3n squared. So it's just n squared plus 2n, and then that upon 6, and you got 2 over here. So 1/12 n plus 1 squared, and then you can take n out of this, so n, and then got n plus 2, which is exactly what we want, right? Look at this thing, same. Okay, now once we are done with this, let's finally go to the main dish, 6th question. So you can already see what kind of, like, this is so complicated, right? So first of all, let me present you a bit of a combinatoric argument that I thought about. So it involves inclusion, exclusion, or maybe let's do that at the last. And first, let me present you with the algebraic argument. So notice that we have nc0, and then you have 2n-cn, right? And then you have 2n minus 2cn. So you can write this as like nc, I mean, in the end, the general term, you can write this as ncr, except the negative signs and everything. You can write this as ncr 2 times of n minus 1 cn. So this thing stays constant, right? And it's like this whole thing is as if it came from 1 plus x to the power of 2 times of n minus 1, right? So maybe like 1 plus x squared, that whole thing to the power of n minus 1, as if it came from that, right? Or it should be n minus r over here, sorry, not n minus 1. Yeah, right? That's how these terms are, right? So it's almost as if it came from this. So the quotient of x power n from this expansion, right? And how do we get this though? So you have r over here, and look, r over, okay, n minus r over here, right? What about this? Ring some kind of bell? I mean, this makes sense, right? What I am getting to is that, in fact, not even that, you just write negative 1 power r, because negative 1 power r is also here, right? So in the general term, you can write this so that you can include the positive negative as well. And now this thing, right, it looks like the term from, in fact, just have this as well, so ncr. So now this thing looks like a term from a binomial expansion. What kind of binomial expansion? Yeah, this thing, 1 plus x squared, so 1 plus x, that thing, whole squared, minus 1 to the power of n. So notice that this will just be nc0, and then you got 1 plus x to the power of 2n, and then you've got negative 1 power 0, so it's positive. And then you got nc1, but negative because negative 1 power 1, right? And then you got 1 plus x power 2n minus 2. So it will decrement by 2 all of the time, right? This power, because it's like 2 times of something that decrements by 1. And then so on, right? And they didn't put till what terms, they just made a dot or dot, and yeah. So the thing is, we were looking for quotient of x power n in this thing, right? So that is what this thing was, right? And this negative 1 power, I mean, that does not contain x anyway. So in the end, we're just looking for the quotient of x power n in this whole thing, right? So the way to do that is just to split this apart like this, and then look for x power n's coefficient in each of these, right? So over here, just have 2ncn, and then that times nc0, right? Which is the first term of this whole thing. And then for the second term, just get 2n minus 2c n, and then minus nc1 multiplied, so the second term, and so on. But in the end, we're just looking for x power n's coefficient in this thing. What is this thing? It's just 2x plus x squared to the power of n, which is like x power n times 2 plus x to the power of n. Now, what's the coefficient of x power n in this thing? It's the same as coefficient of x power 0 in this thing, because this is 1 right here. Yes, that makes sense. And the coefficient of x power 0 in this thing is just 2 power n. Nice. Done. Isn't that right? So the sixth has a really nice algebraic argument, because now this can be extended to a lot many different problems. So wherever you have like this thing is in the normal pattern, but you have something that is not in the normal pattern, and it's depending on whatever the r value is in like nc, yeah, that thing. If it varies with that somehow, then it might be from something like 1 plus x to some power, or like 2 plus 1 plus x to some power, or something like that, right? So these kind of series are also now solvable, or at least we could try to do it like that. So yeah, now we have a good algebraic argument for this thing. Now let's go to the combinatoric argument. So this is the thing that I first thought of while solving it, finding a combinatoric argument. This is not easy actually, but over time I came with it, right? So I gave it like 1 hour or something. I just looked at this problem, gave it 1 hour, and then found an argument. So how does it go? First of all, I thought that you got this alternating positive negative, and this resembles something that we see in combinatorics a lot, which is inclusion exclusion, right? So this is like some number of ways of doing something without a particular restriction minus the ways of doing it with a bit of that restriction applied, and then plus when you apply 2 bits of that restriction, and so on, right? So you have nc0, and then according to that, so according to r, this thing changes, and it changes by 2. So the normal thing is just you have n people. So let's say n is 4, so you got 4 people. So whenever you choose one of these, you will be left with n minus 1. So if you choose r of these, you will be left with n minus r people, but that's not what we want. What we want is to be left with 2n minus 2r people, that is 2 into n minus r people. So n minus r, we already know that, but we just need to make that double somehow. So what if instead of having a straight arrangement of these people, you had some kind of pairing up? So yeah, you had some kind of pairing up. So everyone is paired with a pair, of course, and if you choose r people, so r, let's just say r pairs, then you will be left with how many people? 2 times of n minus r, right? So it represents that thing somehow. And then you have an inclusion exclusion principle as well. So it's like if you choose let's say r people, then in the next r plus 1 you should get negative, and that means in the next one you are breaking some kind of extra penalty, right? So you should not choose the more people in the first step. So you have 2 steps, right? First of all, you will choose r people, and then you will be left with the other 2n minus 2r people, and then from that you will be choosing n people, right? So what should happen is that you will be breaking some penalty if you go for choosing people from the first step, right? And that's why you have this plus minus, something like that. Now I thought about it a lot, and finally what came to my mind is you have n brothers and n sisters, and each of them is a pair. Now the question that we will try to solve is, what is the number of ways uh, to select n people out of these 2n people such that no brother sister pair is in the selection. So you know the number of ways of doing this is just 2 power n, because there's like only n pairs, and out of these n pairs you have to select one, because if you leave any pair, then that means, yeah, you will be left with less than n people in the selection, and that's not good. So you have to choose every single pair, at least one person from every single pair, and you cannot choose two people from a single pair, right? So the number of ways of doing that is just 2 power n, because each pair has a choice, either the brother or the sister, right? So 2 times 2 times 2, n times of this, right? That's why 2 power n is the number of ways of doing this. Now let's go with what this whole series is. First of all, you have nc0. So the way I thought about it is, we'll just choose 0 pairs. So okay, so 0 pairs out of these n pairs, and then the number of if without restriction you had to choose, it would just be 2ncn, right? Yeah, so more like nc0 to ncn. Okay, minus. So if you broke the restriction, in what many ways can you do it? You can have 1 pair, 2 pair, and so on, right? So if you have 1 pair, right, exactly 1 pair chosen, the number of ways of doing this is like nc1, and now just have 2n minus 2 people left. So the number of ways to choose the other n minus 2 people, right? That's going to be 2ncn minus 2. Okay, and fortunately 2n minus 2 nc n minus 2. So fortunately this whole thing is the same thing as 2ncn, right? So that's the number of ways of choosing people with 1 pair involved only, right? That's negative, but of course there can be many other possibilities. So you can have 2 pairs or 3 pairs, and that's why inclusion exclusion principle comes into play. Now you'll have a negative positive alternating fashion. So positive when you break two penalties at the same time. So you chose 2 pairs, right? If that happens, then you just have nc2 and 2n minus 4 cn minus 4. Yes, but that's just cn. And then you got negative nc3 and then 2n minus 6 cn and so on, right? And that's exactly what this thing is. This series is, yeah, so it's the same thing as 2 power n, because we knew from the start that the number of ways of doing this is just 2 power n. So that's the combinatoric argument for this. So this is a great example to show that sometimes the combinatoric argument is actually not good. So I mean, spending time to think about this kind of thing, it's not worth it, right? So instead you should just rely on the algebraic argument sometimes, which is more useful in this case. So yeah, right, now we have the way of dealing with this kind of series. Yeah, so in chapter exercise 6 done. Let's go to 7th. Okay, so this is for some other topic, right? So it's that thing, the floor function video I made involved in the binomial theorem, right? I made a video on it, so it's labeled as, I think it was something like solving a floor function problem by binomial theorem, something like that. Anyway, so that involves this thing, this concept. Right, I will present this through an example actually, and not by actually what they gave us. So right, okay, first of all you just have these remainder things, but I'll just choose specific parts of this exercise to deal with it. So let's do second. Show that the integral part of the number square root 2 plus 1 to the power of 6 is odd, right? And basically we can just figure out what the integral part should be, I guess. So first of all comes the assumption that this is something like an integral part plus a fractional part. Okay, cool. Now the next thing that we'll do is just do the reciprocal of this thing. So 1 upon square root 2 minus square root 2 plus 1, that will be square root 2 minus 1, right? So square root 2 minus 1 is of course less than 1, and that to the power of 6 is once again something that's less than 1 and also positive, by the way. So that will just be a fraction. So positive f dash. So f dash and f are different things. Okay, cool. And now we come to the fact that we can expand this using the binomial theorem. So this will be like 6c0, you got square root 2 to the power of 6 plus 6c1 square root 2 to the power of 5, right? And then so on. This is this guy's expansion, and then you have this guy's expansion, which is just, so 6c0, you got square root 2 power 6 negative 1 power 0, and then you got negative 6c 0, okay, 1 square root 2 power 5 negative 1 power 1, that's why it's negative, and then so on, right? So what happens if you add these two up? Yeah, what happens if you do that? So if we add these two up, you see that these odd coefficient terms, the odd r coefficient terms, those cancel, right? So you can get rid of all of that. And then square root 2 power 6, square root 2 power 4, these are all just even numbers. So this will be like, okay, 2 times of 6c0 square root 2 power 6, which will be like 3. Oh, sorry, 2 power 3, sorry. So 2 power 3, and then you got 6c2 2 power 2, yes, and then you got 6c4 2 power 0, yeah. Oh, sorry, it should be 1 because square root 2 power square root 2 power 2, which will be 2 power 1, and then you got 6c6, which is just 2 power 0, right? This whole thing is the addition of these, which is basically like integer, whatever that thing was, plus f dash. So now these two are positive fractions, and you see that this whole thing is just an integer, right? So, and this is also an integer, of course, and that means this combined must be an integer, and these two are just positive fractions. Or I mean, one of them could be 0 basically, but you can see from here that this it cannot be an integer. That would be very weird. So the only way that this could happen is that, and of course none of these can be 1. So the maximum, like this thing stays in the range 0 to 2, right? Yes, but it's very clear that both of these cannot be 0. In fact, none of these can be 0. I mean, like, of course, this thing is to the power of 6. That's not 0 for sure. So f dash cannot be 0. Even if f was 0, f dash would not be 0. So this combined, right, this thing cannot be 0, and it cannot be 2 as well, but it lies somewhere between 0 and 2. And at the same time, it has to be an integer because this equation must be true. That means f plus f dash must be 1. Isn't that nice? F plus f dash must be 1. So there we go. Yeah, right, f plus f dash must be 1. So now you can figure out what the integer part of this quantity is, because now you have this equation, right? And nothing about it, it's like 2 times some crazy stuff, whatever that is. It's just an integer in the end, right? So 2 times an integer is just an even number, and that minus 1, so I will be this thing minus 1. So yeah, 2 times a number minus 1, that's just an odd number. So I, which is the integer part of this quantity, is just an odd number. So second, we did it, and in fact we even found out what the thing has to be. So this yeah, I mean, it's not good enough, like this is not simple enough to calculate directly, but it is simple enough to show some properties of I, right? So now you can do this kind of question. Let's do the exercise from top to bottom now. Okay, so first question, find the remainder when, okay, let's just not see the answers. It was 3, fine. Now we have to prove that the remainder is 3. Whatever. Okay, so it's not okay, fine, should have not scrolled down that much. Find the remainder when 3 power 51 is divided by 8. So 51, that's like 17 times 3, I guess. You could use number theory to do this. So you can find a quotient of 8, which is supposed to be 4. Yeah. So yeah, I mean, that's one way of doing it. So I mean, you just have to prove that 3 power 4 is something like 8k plus 1, where k is an integer. So it's of that format. Well, 3 power 4 is of course just 81, and then 80 is a multiple of 8. So it's like, yeah, it's just 80 plus 1. So k here is 10 and whatever. Thing is, 3 power 4 is, what do we call it? It's congruent to 1 modulo 8, right? This whole equation can also be written like this. 3 power 4 is congruent to 1 modulo 8. I know, new notation. Don't get scared by this. It's basically this thing, okay? So it's like 8 times something plus 1, that to the power of whatever. So like 3 power 51 can be written as 3 power, let's say 48. So 3 power 48, and that times 3 power 3, right? Now the thing is, you can use the binomial theorem and expand this guy. So all of the 8k containing terms, they will be multiples of 8 in the end. So this guy's remainder is just 1. So it's like this whole thing is just 1 plus 8m, something like that, right? Exactly. 1 power 48 will be the only thing that is not a multiple of 8 in this guy's expansion. And I mean, every term is also an integer, by the way, right? So in the end, it's just this thing, this guy's expansion, it's just going to be 1 plus 8m, where m is some integer. So yeah, and then that times 3 power 3, so 27. 27 is, you can write it as 16 plus 9, I guess. Okay, no, you can write it as 24 plus 3, right? So 24 plus 3. Now 24 is a multiple of 8. That's why I put it like that. So when you do the whole thing, just get 24 times 1 plus 8m. So that's just a multiple of 8. And then you get plus 3 times of 1 plus 8m. So that will be 3 times of 1 plus 3 times of 8m. So notice, this thing is a multiple of 8. This thing is a multiple of 8. So it's like this whole thing is just 3 plus 8n, where n is some, I don't know, some integer, right? So the remainder when 3 power 51 is divided by 8 is 3. We did it, we proved that. And yeah, that's the answer which is given. Now I'm going to present to you a simpler way of doing all of this calculation without ever involving the binomial theorem. So first of all, prime factorize 8. So 8 will be 2 cube. Let's not go with 8. Let's go with normal example. You should really just search up number theory. It will be the most helpful thing while dealing with this kind of questions. But let me just give you an idea of how I do it, right? So you take any, so if you want to find remainder when dividing by some number, you just take that number, you prime factorize it. So for example, you got the prime factorization as, I don't know, 2 power 3, 3 power 2, or 5 power 1, whatever. What you will do is, you will take each prime factor, you will reduce the powers of these prime factors. So that will be 2 power 2, 3 power 1, 5 power 0. Okay, and you will also take each prime factor and do 1 minus. So yeah, subtract 1 from that prime factor. So it's going to be 1, 1, you got 2, and then 5 minus 1 is 4. And then you will multiply this product and that product together. So this will be like 2 power, so 1, and then you got 2, which is 3, so 2 power 3, and then 3, so like 2 power 6. You do 3 into 5 power 0, which is 1. Yes, this thing is called the quotient. So it's the quotient of this quantity, 2 power 3, 3 power 2, 5 power 1. Now, why do we care about finding this quantity? The thing is, any number that is co-prime to this whole number, right? So if you take any number that's co-prime to this number, I don't know, take something like let's say 7. 7 is co-prime to this thing. So 7 has some power of it. So maybe like 3 times 2 power 6 plus 1, if that's the power that this thing has. The thing is, what this actually says, what this quotient actually means is that if you take this co-prime number and raise this to this power, so 3 to 2 power 6, that will just return 1 as the remainder. So that just gives 1 as the remainder. So now if this is like 6 into 2 power 6, so 2 times of that, what we can do is write this thing as 7 times 1 times 7 times 6 into 2 power 6, and then use the fact that this is going to give us a remainder 1, because it's basically it's like 7 into 3 into 2 power 6, that whole thing squared. So it will be 1 plus 3 times, sorry, 1 plus some integer times whatever this number is, that thing squared, which will give us remainder 1. So this whole quantity will be 1 plus some integer times this thing, and then that times 7, right? So it will be 7 plus some quantity times so some number times this whole thing, right? So this will give 7 as the remainder when divided by this thing. Crazy, right? But that's how it works. So this is called the Euler quotient function, and you should really read about this. I have a playlist of Michael Penn in my, yeah, I have played that saved. I have saved that playlist. Please watch all of those videos. These might be really helpful if you want to familiarize yourself with these kind of problems. But okay, it's okay if you don't have that time. It's still doable using just binomial theorem. In fact, sometimes using just binomial theorem gives you conclusions that you would not normally get by modular arithmetic. Yes. But anyway, so with the first question, we did the second question. Next, we have to show that 2 power 2n minus 3n minus 1 is divisible by 9 for all positive integral values of n. Okay, so this is divisible by 9 for all positive integral values of n. Cool. So 2 power 2n, you say, huh? Well, I'm thinking, since you want 9 somehow, you should have something like 3. So maybe that's just 3 minus 1 to the power of, or in fact, let's just write this as 4 power n, and then 4 is just 3 plus 1 power n. Okay, this minus 3n, and that minus 1, right? This is divisible by 3 for all integrals of n. So you can just expand this guy, right? So when you expand this, the term containing highest power of 1, that will be NCN, and then you got 3 power 0 and 1 power n, and then the term before that would have been NCN minus 1, 3 power 1, 1 power n minus 1, and then all of the other terms will contain 3 square or higher, so those will be multiples of 9. So you can just get rid of all of these, so not think about those, right? And then this minus 3n and minus 1, well, this whole thing is just 1, right? Because NCN is 1, 3 power 0 is 1, 1 power n is 1, so this minus 1 will get rid of this thing. And what's this thing actually? It's just NC1, right? This whole thing is just NC1. NC1 is just n, that times 3, so 3n, there we go. 3n minus 3n is 0. So this is all cancelled, and then you just have some terms which contain 3 squares. So 3 squares times some, whatever this thing is. So 3 squares times some integer, some actually really big integer, but whatever. It's a multiple of 9. That's the thing, right? So this whole number, right, we showed that it's a multiple of 9. That's it. Just use binomial theorem and get it done. So in this case, if you would have used quotient for this thing, so it would not have worked because you have unknown values of n, so you can't just reduce it directly. In this particular case, binomial theorem is the way to go, right? But the main reason I'm recommending learning modular arithmetic is because it has many such tricks which are not actually told in, you know, normal syllabus. It's not, yeah, it's just worth knowing. Yeah, you should know it if you can. Okay, or maybe it's just that I knew it and that's why I think it's underrated, but whatever, just keep on going, not think about that. Okay, next is prove that if n is a positive integer, the integral part of this quantity is an odd number. So once again, the same kind of thing. So 4 plus square root 10, the reciprocal of that thing would be 6. Okay, wait, what? It would be like 4 minus square root 10 upon 6, huh? That's weird. So yeah, that is weird. So if this thing is, so this whole thing 4 plus square root 10 to the power of n is something like integer part plus fractional part. Let's just talk about this first. 4 minus square root 10, is this less than 1 somehow? I mean, you can write this as 6 upon 4 plus square root 10, right? Yes, and Is this thing bigger than 6? So is 4 plus square root 10 bigger than 6? Is square root 10 bigger than 2? Well, it is actually, because 10 is bigger than 4. So that means this whole quantity is less than 1, and that means this thing is less than 1. And of course it's positive. So 4 minus square root 10 to the power of n, that will be something that's less than 1 as well, because n is an integer. So if you have 0.5 that to the power of n, that will be like 0 point something less than 5. You get the idea. So it's just going to be fractional part, just the fractional part, no integer part involved in there, right? And then do the same thing, write down the expansions for this guy. So it's going to be nc0 4 power n square root 10 to the power of 0 whatever, and then got nc 1 4 power n minus 1 square root 10 power 1, so on. And then side by side write down this guy's expansion as well. So it's going to be nc0 4 power n square root 10 power 0, and then you got negative nc1 4 power n and then square root power square root 10 power 1, and so on. When you add these up, you will just get all of the terms where square root 10 has power as an even number, right? So the best thing to do is just to add these up directly. So you just have I plus fractional part plus some other fractional. That's just going to be 2 times of this thing. So 2 times of nc0 4 power n plus nc2 4 power n minus 2 10 power 1, right? And so on. So whatever this thing is, it's just an integer basically. So this whole thing is just an even number. What we have to prove is this is an odd number, right? The integral part of this thing is odd number. So do the same thing. This is an even number, so f plus f dash, it must be 1 because it's an integer in the end. So integer plus something is going to be integer. This must be an integer, but then f dash is not 0. It can't be, right? And that means this thing f plus f dash lies in the range 0 to 2. So not included 0, not included 2. There's only one integer that this can be, 1. And that means I is equal to 2 times some integer minus 1, which is an odd number. There we go. This thing is an odd number. Cool. Fifth. Prove that 3 power 2n plus 2 minus 8n minus 9 is divisible by 64 for all n. Once again, something that involves binomial theorem and not number theory. So 64, right? You can write this as 9 plus 1 to the power of n minus 8n minus 9. And from here, it's not hard. I think you can do it by yourself. But still, let's just do it. So the one with the highest power of this one, that will be ncn. You got. Or let's not do that, because this is supposed to be, you start off with the smallest power of this thing, right? Actually, no. Yeah, in the end, you're gonna get the highest power of this thing when you have ncn. ncn, and you got 9 power. 0, and you got 1 power n. Then you got ncn minus 1, 9 power 1, 1 power minus 1, right? So this is just gone. And then plus some stuff that, oh sorry, it should have been 9, and you got 8 plus 1. Sorry. Right? Because 3 power 2 was 9, and then it should also be n plus 1. So it's gonna be n plus 1 right there. Okay, this is slightly wrong. So it's supposed to be 8 plus 1 to the power of n plus 1. That's what this first term is. Now the expansion of this guy will be like n plus 1 c n plus 1 8 power 0. Then you got 1 power n plus 1 whatever, and then you got plus n plus 1 c n, and then you got 8 power 1 plus that times 1 power n minus 1, which is just 1, plus something that has 8 squared, and then all of the other terms will also have 8 squared. Okay, so it's like some multiple of 64. You can just forget about this because that won't come to the remainder anyway. So it's just this thing that might contain remainder, but you also have this, so minus 8n. I think 8n will be better to write here. Minus 8n minus 9. Okay, cool. So this whole thing is just going to be 1. So like 1 minus 9, and then over here you just have n plus 1 times 8, and then minus 8. So this minus 8n, sorry. So this will be like 8. Just 8, yes, and this will be minus 8. So there we go. This whole thing is just a multiple of 64, right? We just did that because this is like 0 plus something times 64, so it's divisible by 64 for all n belonging to natural numbers. Cool. Next, this thing is alpha plus beta where and alpha are positive integers and beta is a fractional part. Prove that 1 minus beta times alpha plus beta is equal to 1. Oh, come on. Right. So let's talk about 8 minus 3 square root 7. In fact, let's talk about it like this. Square root of 64 minus square root of, so 9 times 7, that's only 63, right? So that will be 8 minus 3 square root 7, which will be 1 upon square root of 64 plus square root of 63, right? So this to the power of n, that will be f dash. So like, it's called 8 actually. Sorry. And then you got 8 plus square root of 63 to the power of n is I don't know, I plus f. So I here is in fact just alpha and f is beta, but I just like I plus f, not alpha plus beta. So I'll use this, right? And then the same thing over here, just write down this guy's expansions of nc0, 8 power n and whatever. It's like square root 360, square root 63 to the power of 0 and whatever. And then you got 2 times of this thing because all of the odd r terms will cancel anyway. So yeah, so just exactly. So from this you can say like all of this is just some kind of integer. So integer is equal to integer plus fractional part plus fraction, some other fraction part. Same thing as before. This thing will be 1. So f dash is just 1 minus of f. In their language is going to be 1 minus beta. Right. So basically 8 plus square root 3, square root 63 to the power of n is alpha plus beta, and then 8 minus square root 3 to the power of n is 1 minus beta. So now what you have to prove is multiplication of these two equations just gives us 1 on the difference, which is like obvious because it's just 8 plus square root 3 times 8 minus square root 3, all of that is 1 n. And then yeah, that multiplication is just 1 power n, so it's 1. So 6 is done. Just wait a second. Okay, 6 is done. Let's go to 7. N belonging to integer and 7 plus 4 square root 3 power n. So one thing is like square root of 49 and you got square root of 48. So the same thing as this except with different numbers. Yeah. So it's equal to I plus f, where I is the integral part and f. Come on, seriously, it's the same thing as the previous question, just with different numbers. It's gonna be the same thing. F plus f dash is equal to so in this case it's gonna be capital F plus small f dash, whatever. That's equal to 1. So the fractional part of 7 minus 4 square root 3, that will be 1 minus capital F, right? And notice that 7 plus 4 square root 3 and 7 minus 4 square root 3 multiplied to 1. So it's all good, right? You can just multiply it latently and you get 1 on one side, and then I plus f, which is this thing, that times of 1 minus f on the other side. Exactly. So I won't even write down what equations we have for this. 7th is, I mean, it's just repetition of 6th once again. 8. What are the last 3 digits of 7 power 100 minus 3 power 100? So since we want the last 3 digits, we should take the remainder by 1000, right? Because 1000 is like 1000. So only the last 3 digits will survive. All of the other things just has 1000 in there, right? So when you do the place value expansion for a number, all of the terms that contain 1000 or higher, those will be neglected. Just got the other, the remainder basically when divided by 1000, right? So want to divide by 1000. What's the last 3 digits of this thing? You could of course just take the quotient, right? And that will do it. Or I mean, there's a better way of doing it. Should I tell you this? Whatever, just do this. So I can write 1000 as 2 power 3 times 5 power 3. So we'll first of all figure out what the remainder is when we divide this quantity by 2 power 3, that is 8, and when you divide this by 5 power 3. Why am I doing this? We'll see what I'm doing in the end. Okay, so when you divide this by 2 power 3, what's the quotient of 2 power 3? It's going to be 2 power 2 times 2 minus 1, which is just 4, right? Yeah, exact. I mean, this is yeah, of course. So like what it's saying is that this whole thing is just a multiple of 8 because I mean 100 is a multiple of 4. So it's like, yeah, the quotient of 2 power 3 is just 4, and then 7 power 100 is like 7 times, so 7 up to the power of 25 times 4. So this will just give us 1 when you divide this by 2 power 3, right, as the remainder. And then 3 power 100 will also give us the remainder 1. So it's like 1 plus 2 power 3 times something, so some integer, and then minus 1 plus 2 power 3 times some other integer which is like smaller than this integer. So in the end it's just 2 power 3 times some other integer, right? So yeah, this whole thing is just a multiple of 2 power 3, right? And in the language of model arithmetic, what we say is that 7 power 100 minus 3 power 100 is congruent to 0 mod 2 power 3 is just 8, and then 5 power 3, let's do it with that. So quotient of 5 power 3, that's just going to be 5 power 2 times 5 minus 1, so it's like 4 times of 25, which turns out, yeah, I mean, it's just it's just 100, isn't it? So 7 and 3 are co-prime to 5, and then once again 7 and 3 are also co-prime to 2. That was the condition, right? So it's also co-prime to 5 or 3, of course, and that means, right, it's just like some co-prime to the quotient number, it's just 1 congruent to 1 modulo 5 power 3, right? I mean, basically it has remainder 1 when divided by 5 power 3, both of these things, 7 power 100 and 3 power 100. So their subtraction will have remainder 0 when divided by 5 power 3. So yeah, the thing is, this whole quantity is just a multiple of 1000. Look, the thing is, 7 power 100 minus 3 power 100 is a multiple of 8. So it's 8 times some integer. And then 7 power 100 minus 3 power 100 is also a multiple of 125. So 125 times some other integer. So what will this be? I mean, like, it's a multiple of 8 and also 125. So in the prime factorization of this thing, you have at least 2 power 3. You could have 2 power 4 or 2 power whatever, but you have at least 2 power 3, and then you also have at least 5 power 3, and that times some integer. That's the thing, right? That will be the prime factorization of this thing. You can factor out a 2 power 3 and 5 power 3 from it, which basically says that 1000 times some integer. So this whole thing is just 1000 times some integer. It's multiple of 1000. So the last 3 digits of this thing is just 0, 0, 0. Nice. So 8, we can do it. Okay, you can already see the answer, can't you? Okay, so answer key 8000. Fine. So 8 was I mean, without the knowledge of model arithmetic, this would have to be done using binomial theorem, which let's just say it's kind of complicated to do it like that. You could do it, so you can write it as 10 power, so 10 plus 3 to the power of 10 minus 3 to the power of 1000, and then minus 3 power 1000, and then do the whole expansion. So just figure out the last 3 terms of this thing, so that will contain, so we'll have 3 power 1000, right? So actually negative 3 power 1000, which is just 3 power 1000 anyway. You got 10 power 0, and you got, well, 1000 C 0, which is actually just 1. And then you have 10, and then 3 power 999, okay, negative, and then you got 1000 C1, which is just 1000, right? That's the other thing. And then you should have the next 2 terms as well to actually figure out anything. So the next term will also be involved, but the next term, I mean, so 1, 2, 3, 4, the fourth last term, this thing will contain 1000, and then all the terms after this will contain 1000, because 10 power 3, 10 power 4, whatever. And so you can neglect all of these terms, but you will need this other term. So just write down what that is. It will be positive, and it will be like 1000 C2. That will be 1000 times 999 upon 2 is like 500 times 999, whatever that thing is. Okay, that is 10 power 2, and then 3 power 998. So all of this will be the expansion of 7 power 100, right? And then this minus 3 power 100, so it will kill away this thing. And you notice that this and this, these things make all of this a multiple of 1000. So you're done. Like, all of this expansion will be a multiple of 1000. So this thing is a multiple of 1000. Done, right? So you can do it using binomial theorem as well. Okay, 9th question, show that 13 power 99 minus 19 power 93 is divisible by 162. Fine. So first of all, prime factorize one. Okay, maybe prime factorizing. Yeah, just do it. Prime factorize 162. That will just be 2 times of 81. So it's like 2 times of 3 power 4. So you could do the quotient method that I just told you. Or, I mean, okay, I just want to show it the proper way without using that, but kind of hate it. I hate to do it like that. The way to do it is just figure out the remainder when it's divided by 3 power 4 and by 2. So when you are wanting to show that it's divided by 3 into, 2 into 3 power 4, you just show this divided by 2, that is, it's even, which actually it is. I mean, it's just 13, which is odd, which is an odd number at the power of 99, minus another odd number to the power of 93. So it's just odd minus odd, which is even. So this 2 part is done anyway. 3 power 4 is the other part that you have to do. So this is a multiple of 3 power 4, like 81. And that is actually hard to prove without, using model arithmetic. So 13 and 19, both of these are just not multiples of 81, right? Now the quotient of 3 power 4, that will just be 3 power 3, which is like 27, and that times 2. So that's going to be 54. So you can just cancel out the factors of 54 from these powers. So it's going to be like 54 times 1 is just 54. 54 times 2 is 108, which is already bigger than these things. So you can get rid of those things. So I mean, yeah, just get rid of one of these 54 things. So it's going to be 13 power 50. So okay, that's gone, right? So 45, and then minus 19 power. So you get rid of that 54. It's going to be 30 minus 4 is just, what's 30 minus 4? 30 minus 4 is just 9. What am I doing? Sorry. Yeah, actually, it's correct. Sorry, 30 minus 4 is just 9. And then you got 8 minus 5 is 3. So this is what it will reduce to. And yeah, at this point, how do we do it? How do we go ahead now? Because we exhausted this thing to whatever small value we could get, and now it's still not doable. So this didn't work, right? The quotient is 54, and that makes it actually hard to use. You will have to just basically start squaring this or do something like that to actually get the idea. So 45 is like 3 times of 15. So 13 cube might be something that you would try to, get, right? Or, you can just write it like, I don't know, 12 plus 1 to the power of 45, then minus of 18 plus 1 to the power of 39. I know this is kind of hard to expand this directly. So you want 3 power 4 at least. This is a multiple of 3. Yes. So its 4th power and everything that will be gone. Yes. Okay, that makes sense. So you could do the binomial theorem thing after this. So that, yeah. Or you could actually directly do it with 99 and 93 as well. I mean, of course, it's binomial theorem that all of these questions are based on, so it won't always involve modular arithmetic. Most of these did involve just binomial theorem. So okay, let's go ahead and do it from the start now. Because now that we know it can be done easily, it's just like 20 plus 1 to the power of 99 minus 18 plus 1 to the power of 93, right? So this whole thing, you have to show that this is divisible by, well, basically 3 power 4, so 81. Right, so write down this guy's expansion. Yeah. So let's start off at let's just go the opposite way. Let's write this 1 plus 12, so that you don't have to go backwards. But I mean, even going backwards is not a big task. Okay. 99C0, and then you got 12 power 0, so just 1. You got 99C1 times 12. But 99C2 times 12 squared. At this point, you have 3 squared over here. You just need to go one more term. So 99C3, and then you got 12 cubed. So now you have 27 right here. And then the next term will have 12 power 4, which will be basically 3 power 4. It will contain 3 power 4. So you can get rid of all of the other terms because those aren't actually that important. And then let's do this thing. So it's going to be minus all of that minus this thing. So it's going to be 93C0, and then you got 18 power 0 whatever, and you got 93C1 times 18, and then 93C2 times 18 squared. So you have to stop here because now this thing just contains 3 power 4. So all of the other terms will also contain 3 power 4. So you can get rid of all of that. So it's just this minus that. Yeah, this is complicated because now you have to calculate all of this by hand, and that's not good. So you know what I'll do? I'll just write 12 as 3 times of 4. Okay. And yeah, doing that, what you can do, I mean, you can just write this whole thing as well, 3 power 3, and then you got 4 power 3. So 4 power 3 is just 3 plus 1 power 3, right? Yes, so it's gonna be like 3 power 3, and then the thing is, you will get rid of all of the things which have 3 power 1 or higher in the expansion of 4 power 3, right? It's like 3 plus 1 power 3. I know, doing it 2 times, it's kind of lengthy, but anyway, it's gonna be like 1 plus something that involves 3. So there you go, you can get rid of all of that. Okay, similarly, 12 square, I mean, like, okay, 12 square is just doable directly. It's like 144, and then 144 minus 81 will be the remainder thing. But the thing is, like, it's got 99C2, which is not good, not good. So what we could do is just write down 99 to 98, and that upon 2, right? Well, this thing is just an integer, and then you got 12 squared right there. So it's like 3 power 2 and then 3 power 2. So this whole thing is just exactly, this is just a multiple of 3 power 4 anyway. So you can get rid of this whole thing directly. This will not be directly a multiple of 3 power 4. What about this guy? So you had 3 power 3 from this guy, and then 99C3 is just 99 into 98 into 197 upon 3 into 2 into 1, right? So 97 is not a multiple of 3. This is not a multiple of 3. This is a multiple of 3. So the power of 3 in this guy, that will just be 3 power 1 because 9 upon 3 is 3. So 3 power 1 times some other integer. So this will be like 3 times of 3 power 3, which means this is also just a multiple of 3 power 4. So you can get rid of all of that. Now we are just left with this 99C0 and then 99C1 times 12. So that's just 1 plus 99 times 12. Yeah, and then like, yeah, exactly, 99 times 12. Oh, sorry, battery low. Wait, but it's already on. Okay, what was missing? Okay, so the thing is, we just want the remainder when it's divided by 3 power 4. Oh, and of course, like this thing, this whole thing minus all of this stuff. So it's also got that 1 right there. So you can get rid of this 1 directly, and then you got 93C1, so like 93, and that times 18. So this thing minus that, right? Is this a multiple of 81? That's the same as asking is so you can just take some 3 power stuff out, so like 3 power 2 out. You just got 9. It just got 11, and then 11 times 4, and that minus. So 2 times of 93, right? Oh, you also have a 3 over here. Okay, this is really awesome. So wow. But this unfortunately does not have. Okay, you also have 12. Sorry. So you took. In fact, you can just take 3 power 3 out in that case. So 3 power 3 out, you got 11 times 4, and then that minus 31 times 2. Yes. Now this thing must be a multiple of 3. That's all you have to prove, which is easy. So like it's going to be 44 minus 62. Is this a multiple of 3? That's all you have to prove. So like it's just going to be negative of 8, and then 5 minus 4 is so 8. Well, yeah, it's a multiple of 3. Done. 3 power 3 times something multiple of 3. 3 power 4. So you are done. So you proved that this whole thing is also multiple of 3 power 4, and also it's even. So that means it's a multiple of 162 basically. So 9th is done, huh? Yeah. So 7th done. You can finally start 1A now. So I will do that in the next video. So see you guys in the next video. Bye.